This video is going to cover simplifying radicals. The approach that I'm going to take is a little different from most textbooks, but I think it has two advantages. One advantage is that a student doesn't have to have a large base knowledge of square numbers. Because let's face it, how many students know that 14 squared is 196 right off the top of their head? Not many. The other advantage is that students do not need to have a large base knowledge of factors and be able to divide large numbers by other large factors. My method is going to use prime numbers and a prime factorization, and then a method of grouping the digits together and then pulling them out of the radical or leaving them under the radical. So the best way to show you is just to get started with an example. The first example that we're going to use is the square root of 24. Well, before I can continue, I need to find the prime factorization of 24. And the way I'm going to do this, I'm going to use what I've called the stair-step method. I'm going to take 24 and put them down at the bottom, and we're going to work our way up. And you'll see that it kind of forms some stair steps. And I'm only going to divide prime numbers out of here. So 2, 3, 5, 7, and so on. So the first prime number that I'm going to try taking out is a 2. And the reason I'm going to do this is because 24 is even. So as long as this number is even in here, I'm just going to keep pulling out 2's. So 24 divided by 2 is 12. And 12 divided by 2 is 6. And it's still even, so 6 divided by 2 is 3. Okay, now 3 is no longer even, so I can't divide it by 2. But, 3 is a prime number though, so I can divide it by 3. And the goal is to get a 1 at the very, very top. And once I get that 1, I know that I'm done. So the prime factorization of 24 is 2 times 2 times 2 times 3. So I'm going to rewrite this radical using the prime factorization of 24. Because square roots have an index of 2, I'm going to be taking out pairs of numbers. Other higher indexes, like cubed roots, would have a 3 for its index, or a fourth root would have a 4 for its index. And we'll get to those problems later. But for now, we're dealing with square roots, roots whose index is only 2, and this is how we're going to deal with them. We're going to pair up like numbers. So here's a pair of 2's, and what's left is just 2 and 3. There are no more pairs, so the 2 and 3 gets left inside. So let me explain it to you this way. My junior high students really like it this way. Okay, you can pretend that this radical is like a prison. You can call it radical prison. And it takes one guy and his buddy that's just like him in order to make it out. So it takes a pair to make it out of the radical. But when they get out, something bad has happened and one of them doesn't make it out. So we have one pair, but the pair itself doesn't make it out, just one of them does. So of these two 2's, one of them makes it out. Well, what happens with the other ones? Well, they're still left inside there. So what's left inside is 2 times 3, and we're just going to multiply those numbers back together, and 2 times 3 is 6. So, simplified, the square root of 24 is 2 radical 6. The next example I want to do is the square root of 72. So the first thing we need to do is find the prime factorization of 72. So I'm going to put it down here and start dividing out prime numbers. Well, as long as it's even, I'm going to still divide out 2's. So 2 goes into 72 36 times. 36 is still even, so let's pull a 2 out, and we get 18. 18, still even, so I'm going to pull a 2 out, and now I get 9. Well, 2 won't go in there anymore, but I know that 9 is divisible by 3, so I'm going to divide it by 3 a couple of times, and I'm left with 1 at the very top. So I know the prime factorization of 72 has 3 2's and 2 3's. So I'm going to rewrite my radical now as 2 times 2 times 2 times 3 times 3. So I'm going to do this pairing method now because my index is 2 because I'm taking the square root. Well, here's a pair of 2's and here's a pair of 3's. So the 2's will come out and the 3's will come out. So on the outside now I'll have written 2 times 3. Well, this 2 right there didn't have a buddy, so he stayed in there, and he's all by himself. So now we're going to go ahead and multiply these numbers together that are on the outside. 2 times 3 is 6, and it's 6 radical 2, because that 2 was left on the inside by himself. So the square root of 72 is 6 radical 2. Another nice thing about this method is that it even includes ways to take square roots if there's variables involved. So we have 60 as our number, so I'm still going to find the prime factorization of 60. Take a 2 out, and half of 60 is 30. Take another 2 out, we get 15. Take a 3 out, and we get 5. 5 is also a prime number, so we can do that. So the prime factorization of 60 is 2 times 2 times 3 times 5. So I'm going to rewrite this expression as 2 times 2 times 3 times 5. And how many y's do I have? Well, I've got y cubed, so there's 3 y's in there. So once you get better at this, you're not going to need to write out all of your variables, but I'm doing this just so you can see the pattern, and then you'll be able to make shortcuts on your own. So again, we're taking the square root, so I'm going to take out pairs of numbers. Here's a pair of 2's, and here's a pair of y's. So my 2's make it out, and my y's make it out, but only one of them makes it, so I had a pair of 2's and a pair of y's, and everything else that gets left behind stays, and I just multiply them back together. So the 2y was out, and 3 times 5 is 15, and the 15y stayed in. So the square root of 60y cubed becomes 2y radical 15y. Now, as I mentioned before, another advantage of this method is that it also covers higher roots. In this case, we're taking the cubed root of 54. Well, so like every other time, the first thing I want to do is to find the prime factorization of 54. 54 is even, so let's take a 2 out. And I'm left with 27 now. Well, 27 is divisible by 3, and you get 9. So I'm just going to work my prime factorization until I get 1 at the very top. So I know now that 54 breaks down to 2 times 3 times 3 times 3. In this case, we're no longer taking pairs of numbers out, but we're actually taking triplets out because of our index of 3, the cubed root. So now I find 3 of a kind, and this group of 3's makes it out, but on the outside, only one of them makes it. So what I have left over is the cubed root of 2. So the answer for the cubed root of 54 is 3 times the cubed root of 2. Another example is the fourth root of 81. So this time our index is 4, so instead of taking pairs or a group of 3, I'm actually going to take a group of 4. So, as before, let's start with 81 and find the prime factorization of 81. Well, a 3 will divide out of 81, and you'll be left with 27. Another 3 will divide out of it, and you get 9. Another 3 will give you 3, and one final 3 will give you 1. So what we have here is really the fourth root of 3 times 3 times 3 times 3. So, again, because our index is 4, we're taking a group of 4. Well, we've got 4 3's right there, so I want all 4 of them, and they'll go out, and they'll make a real 3 on the outside. And now, is there anything left inside here? No, there's nothing left. So if there's nothing left, there's no reason to put your radical. So your final answer is just 3. Our final example will be the cubed root of 588 x to the 5th. So, like before, we're going to start with 588, and we're going to work at finding the prime factorization of him. Well, I know that 2 will go into him because the last digit is even, and that gives us 294. Well, I know that 2 will still go into that, so that'll give me 147. Well, 147 is one of those numbers that sometimes we have troubles doing, but I know it's divisible by 3 because 1 plus 4 is 5, plus 7 is 12, and 12 is divisible by 3. So I just used my rules of divisibility to know that 3 could divide 147 evenly. And what do I get when I do that? I get 49. Hey, well 49 is a good number because I know 7 will go into 49 twice. So let me rewrite this whole thing, and this is going to be a big one. This is the cubed root, and I have 2 times 2 times 3 times 7 times 7, and I have 5 x's. Okay, so I've got a whole string of numbers here, and we're finding groups of 3 that we want to take out of there. Well, are there any groups of 3 with my numbers? Nope. Oh, only my x's have a group of 3. Well, so I'll have one x that makes it on the outside, and actually everything else gets left in there. So cubed root of, when I multiply all these back together again, I get 588. I know that because that's where that came from. And then x squared, because there's 2 x's left over. So that one wouldn't simplify very much, as some examples won't. So the cubed root of 588 x to the 5th simplified to x times the cubed root of 588 x squared.